As always, we start with a brief recap on inverse kinematics and trajectory following. In the last lecture, we introduced the idea of having the robot not follow the line on the floor, but waypoints, which is a very general way to control not only mobile robots, but also robotic arms. And the idea is to set a number of waypoints, compute the error from the robot's current pose to the pose of the next waypoint on the list, and then use a so-called feedback controller to drive the robot to the waypoint. When considering a mobile robot, the error can look like this. We have an error in distance, which is the Euclidean distance between the goal position and the current position, which is denoted as rho here. We have an angle of orientation that the robot should have in order to drive toward the goal. This is computed by using the arcus tangens of the distance in x and the distance in y coordinates minus the current orientation of the robot. Now, why is there a minus sign here? Well, the current orientation of the robot is negative because the direction of positive rotation is counterclockwise due to the right-hand rule. The x-axis of the robot coordinate system is parallel to the x-axis of the world coordinate system, and the robot currently faces into a negative angle orientation. Finally, we have the error in the final heading, which you can see here. So these two angles, the desired goal heading and the current angle of the robot, are added. Now in this case, we have again a negative angle of rotation, so minus gets plus in this case, and we get this equation here. We have then argued that you can simply follow your intuition to come up with a controller to drive the robot to that position. In this case, consider this example here. The robot is facing 90 degrees to the north. The object is at a minus 45 degree angle. Why minus 45? Again, the positive rotation direction is counterclockwise in this coordinate system, so the robot has to turn by a negative angle of 45 degrees, which we have here. Now, in order to turn this way, the left wheel has to turn faster forward and the right wheel has to turn backward. So we argue to simply use the angle orientation error directly in computing the wheel speed. So we use negative alpha for the left wheel and positive alpha for the right wheel. Now, once alpha is 0, the robot stops turning, and we add another term which is proportional to the distance rho, which makes the robot turn toward the goal. Now in this case, the robot will do both at the same time. It will both turn and drive a little bit, and by tuning these parameters accordingly, you will be able to tune the behavior from driving either in a big curve and very fast to turning very abruptly and then driving directly to the goal. We also introduced the idea of switching mode control. You can choose between different behaviors. For example, here we say if rho is larger than 3 centimeters, we choose behavior A, which might be this controller here. Once you are closer, we might choose behavior B, which would then adjust the final goal heading. Now we introduce the topic of today's lecture, which is differential kinematics and control. For this, we have to go back a little bit and recall how the forward kinematics of the mobile robot were computed. We came up with this idea to say you can't really tell where the robot is by just looking at the position of its wheels, but when looking at a small increment, which we use the symbol delta for, a small increment of the left wheel or a small increment of the right wheel, we can compute a small increment of forward translation. Likewise, we can, by looking at small increments of the wheel speeds, or the wheel rotations in this case, we can compute small increments in rotation. The reason for this has been holometry. The mobile robot is what we call non-holometric, and just to recall this, for systems that are holometric, you can actually tell where the robot is based on the orientation of the actuators. If you look at a robotic arm, you will see, let's say you start at 0, 0 for both of its motors. You can drive a curve in the configuration space where we return to 0, 0, and the robot will also return to its origin. So this is the robot here. The black lines are the robot at 0, 0, then it does its motions as depicted here, then finally returns to 0, 0, and it ends up at the same location. This is not the case for a non-holometric platform. Here we have the configuration space of a differential wheels robot with 2 wheels. We show the actual angle of rotation for each wheel. We start at 0, 0, then the robot drives straight, then makes a turn, and finally the wheels end up at 0, 0 again. Now, does the robot return to the origin of where it started? No. When you draw this out, you will see the robot drives straight and then makes its turn and then wobbles a little bit back and forth, but it doesn't return to the origin. So just looking at the positions is useless. What we have to do is we have to look at speeds. Now we can actually move on from the delta notation and introduce using derivatives. In this case, this equation looks like this. So we have the derivative of distance is given by the derivative of the wheel orientation. And as you remember, the derivative of a distance is speed. So we have the wheel speeds, and from that we compute the speed of the robot in its x frame and its rotational speed omega z dot. The notation using the apostrophe is equivalent to putting a dot over the variable, which you might be more familiar with. In this lecture we're using both notations. Now you can also do the inverse. These are still just variables, so even though these are speeds, I can now convert from Cartesian speeds to wheel speeds by just inverting these equations. And now already here you see that they look very familiar to the controller that we have been implementing. So you see here we have a positive contribution of the distance. Here we have a positive contribution of the forward speed, and then we have a negative contribution on the left wheel of the angular orientation, in this case the angular speed, and the opposite for the right wheel. Now we would like to understand a little better why this is and why these things are looking so similar, and for that we have to look at minimizing error in a very general way. When you have a function, you can find its minimum using analysis, and very often these kind of functions are some kind of error function. In that way, they are very similar to the error we have defined for the position of the robot, and we will see that the ways of solving them numerically are very similar to implementing a robot controller. So when I say numerically, what I mean is to find the programmatic way to find this minimum. So I'm not talking about simply taking derivative, setting it to 0, but I'm talking about some kind of black box where you are not given access to the function itself, but you just have ways of evaluating the function at different points. So the picture here to the bottom shows a 2D cost function which has a value or minimum in the center, and the idea is to sample this function at different positions at different times. So I'm starting here and then I'm moving step by step toward the center of this valley. Now, how is this done? Let's do it numerically for a more complicated function like this one, which is a parable which is shifted by 2, and you can now see where the minimum is. It is at the coordinate 2. How do we find it? We can take the derivative, which is 2x minus 4, also written down here, and you can plot the derivative, which is this red line. So you see the function is a parabola and the derivative is a line, and we know that the parabola will have its minimum where the derivative is 0. So in this case, this is also where the gradient crosses the x-axis, which is right here, and as this is a line, as we can now see, we see that the gradient is positive whenever you are to the right of the minimum, and the gradient is negative whenever you are to the left of the minimum. What this means is that when I sample the gradient of the error function at a random point, I know already which direction I have to go in order to meet the minimum. If it's negative, I have to go to the right. If it's positive, I have to go to the left. That means also I can just follow the gradient in the negative direction and I will get closer to the minimum. Now let's do this for a couple of numbers, and here I have a table where k is the time step of my iteration, or the iteration number, x is the value that I'm choosing to test for my minimum, and f apostrophe of x is the value of the derivative at this point. So when I take the value minus 2, the derivative is 2x minus 4, so the derivative is minus 8. I then move further to the right until I converge with the minimum. Now, I told you the idea is to move along the negative direction of the gradient. So I came up with the following update rule. I say that x of k plus 1, so my guess for the next iteration, is my previous guess minus the derivative times some learning rate. So the learning rate is important because when I would just move to the right by minus 8, I would really jump far ahead of the minimum. So what I should do is I should try with a smaller number, let's say 0.1, and we can now try what happens when I do this. 0.1 times minus 8 is minus 0.8. Now using this equation, minus 2 plus 0.8 is minus 1.2, and that gives me the next point where I want to try to move to the minimum. So if I do that and I evaluate the derivative, it is minus 6.4. 0.1 times minus 6.4 is minus 0.64. I can subtract that from my current value and I'm getting to minus 5.6. Now you see the pattern how this is done. You can maybe spend some time following this some more, but what you will see is that the steps with which I move become smaller and smaller, and I end up moving or converging slowly to the minimum, which we do now is at 2. How can we speed this up? Well, we could increase the learning rate. In this case, I try the learning rate of 0.4, which is 4 times as much. Now, minus 8 times 0.4 is 3.2. I can subtract that from minus 2. I'm getting 1.2, and you can see that that way I converge to the minimum much faster. In only 4 steps, I'm very close. I'm at 1.9936, and as I go on, I will eventually approximate 2. and the derivative is going to be 0. Well, what happens when I further increase the learning rate? In this case, I'm making huge steps and I'm overshooting the minimum already at the first step. I'm ending up at 2.8, which is too high. And my approach, of course, also works the other way around. I will just now move to the left and I end up at 1.84. And then in the third step, I'm very close to 2. So this is a picture that shows the different behaviors that I can expect. The idea is that the input happens at time 0, where I tell the robot to the new goal. So the robot is currently here, but I want it to be there. And I'm now looking at the error as it evolves and as the robot approaches the desired set point. The first things we've seen is some slow convergence toward the goal, toward the minimum of our function. When I start increasing the learning rate, or increasing the gain, as we would say in this scenario where we talk about a controller, you saw that the estimator overshoots and then goes back, undershoots and then overshoots again, eventually converges. Now, as we further increase the learning rate, we will first see some marginally stable state where the error just jumps back and forth. If we then further increase it, it will become unstable by either building up the error exponentially and oscillating, or just going through the roof directly. This is also why I showed you how the error is derived for a function in a numerical fashion, because you can very easily see exactly the behavior that you would see in a robot scenario. Now, when you did this experiment in Weebots, you have probably only seen this behavior here. I have then asked you to increase the gain quite tremendously, where you got into a marginally stable situation where the robot just turns back and forth, back and forth. Now, the robot isn't fast enough to exhibit this kind of overshooting behavior, because we are only giving it 32 milliseconds. If you would increase the time, the sampling rate of your controller, you would be able to see other behavior, including this one, because then the robot would have enough time to actually overshoot and then turn back. So I let you play with this a little more on Weebots. Now let's go back to the error function that we are truly interested in minimizing, which is the error of the robot. We have been introducing a polar coordinate frame error, rho, which was the distance, and alpha, which has been the angle. Now let's introduce a quadratic error term like E equals rho square plus alpha square and try to find the minimum. Now, what can we change? We can change x dot and theta r dot. So we are interested, which is the forward speed of the robot and the rotational speed. And so we know that the change in x should be proportional to the derivative of the error with respect to the rho. And in this case, we can drop here the second term, and we will have just 2 times rho times the inner derivative of this term with respect to x. This is a little complicated because we are using Cartesian coordinates here, and this is in polar coordinates. Let's not get too deep into it, but the intuition here is that the minus sign will cancel itself out, and we will end up with a term that makes x dot to be proportional to rho. When you look at the angular error, same thing. We take the derivative of the error term with respect to alpha. And in this case, alpha and theta is related. Now we will get a negative, we will get a term which corresponds to 2 times alpha, and we have the inner derivative, and you can see that the minus sign is coming from the tether r term here being negative. So this will be multiplied with -1, and the result is that tether r is gonna be proportional to alpha. And with that you get the equations for the wheel speed after converting from polar coordinates into wheel speeds. And these will be very similar to the intuitive controller that we came up with. So when you look at proportional control, the advantage is that the larger the error, the bigger the movement, but at the same time the controller gets very slow as we approach, because if the error is very small, the movement gets very small. Now what can you do? You can crank up the gain, but you will very quickly get into some kind of overshooting behavior, which is highly undesirable. And you will get to a steady state error due to the deadband effect, which is that the robot will simply not move if the speeds that you set are too small, especially if it already came to rest. Now there's a way out of this, which is the so-called PID controller. And here the idea is that you combine different error terms, and in this case we use drawings like this, where you have the robot, also known as the plant or the process and controls here, and you observe a desired output. You have a set input here, and subtracting the two from each other gives you the error signal. And now you already know the proportional term. You take the error and multiply it with a certain gain, and that gives you the control signal that you sent to the robot. Now in PID control you add two more terms to this, and one is proportional to the integral of the previous error, and the other is proportional to derivative of the error as it emerges. Now the integral term is easy to understand if you think about this deadband effect and the problem that you will end up with a steady state error. Now if you just keep adding up this very small error over the last 5, 10 or 20 time steps, at some point the sum of the error will become big enough to create a control signal that will actually move the robot. So when you use an integral term, you can really avoid this steady state error. At the same time, you want to speed up the controller to get to the desired result, and so you say the further I'm away from my error, the faster steps I can go. So as the error becomes changing very little, you add very little to your control input, but in the beginning, as the error is changing quickly, you can move in much faster steps. So what you get is you get an increased speed of convergence and no steady state error. Of course, tuning these three values is a lot more complicated than it has been with P control, but what you can do is you can start with a P controller, then introducing the additional terms and slowly reducing the P value, and see how you can tune the behavior to be better than a basic P controller. Now I promised you the differential kinematics is a very general approach that works not only for mobile robots but also for robot arms. And what I propose to you is that there's some kind of matrix, which we will call the Jacobian matrix, that will relate wheel speeds or speeds in the actuator space to speeds in the Cartesian space. So in this case, we have the 6 degrees of freedom to the left here, which are the 3 translation speeds and 3 rotations speeds. Now on the right side, we have the angular speeds of a robot arm or a mobile robot. And when you look at the matrix here, you will have 6 rows and as many columns as you need for the actuators. So in case of the mobile robot, we only have the x dot component and the omega z component, which are 2 rows in the output, and in the input we will have only 2 rows for the 2 motors. And so in this case we would have the partial derivative of x with respect to phi left dot, and then we have the partial derivative of x with respect to phi r dot. Now, in order to do this, let's look at these equations and take those derivatives. So the derivative of x with respect to phi l is r divided by 2. This term goes away, and we put an r divided by 2 here. The derivative of x with respect to phi r dot is r divided by 2 as well. And when you do this for omega, you will get r divided by d here for the right wheel speed, and minus r divided by d for the left wheel speed. Now, if you multiply this matrix out, you will see that you get exactly these equations. And I hope with that you see how this idea of having a Jacobian matrix which contains all these partial derivatives is actually exactly what we have been doing when we analytically derived those equations for the forward kinematics. Now I can invert the matrix. In this case I have the Jacobian, and I take the inverse in order to turn the desired speeds in Cartesian space into wheel speeds. So in order to do this, I used a simple equation that gives me the inverse of a 2x2 matrix. Inverting other matrices is more complicated or might require a numerical approach, but I have used this simple one here, and the inverse of this is that. And now if you work out those equations, you will see that they again turn out to be exactly the equations that we have derived for the inverse differential kinematics to drive the robot to a certain velocity in Cartesian space. So now the Jacobian is nothing else than a gradient that you can use to optimize a function, except that it is a multidimensional gradient. And what you can say for robotic systems is that the change in the actuators that you want to put is minus the gradient times the error, much like we have derived earlier for the controller. And when you look at this for the mobile robot, you will again come to the same equations that we have derived previously. We have the error terms here, rho and alpha, and we use the inverse Jacobian to get the wheel speeds. So what you've seen so far is a little bit of background on why the controllers that we've been deriving intuitively actually do work. They are derived from the idea to optimize a function. In order to really understand how this works and to formally talk about stability and convergence behavior, you will need to take another class like feedback control of dynamic systems. This is the textbook I've used when I took that class. It does require frequency domain analysis and other tools that more are in an ME or electrical engineering curriculum, rather not in computer science. But I hope that this intuition and tools will be sufficient for you to implement basic controllers. Especially what you've seen today on the differential kinematics directly applies to robotic arms, like the universal robot arm here with 6 degrees of freedom. And you can relate the speeds in the angular velocity at each of these joints to the speeds of the n effector, and you can also invert that relationship and then use it in a feedback control scheme to drive the robot to a desired location. So in summary, non-holonomic systems require looking at their velocities, not the actuator positions, which is known as differential kinematics. We can then use these velocities in a feedback control scheme which is very similar to numerically minimizing an error of a function using what is called gradient descent. In particular, you will see the same behaviors when you do that as if you use a robot, namely overshooting and unstable behavior if you are trying to go too fast. We also introduced the general form of differential kinematics, which is known as the velocity Jacobian. I hope I showed you how the mobile robot that we've been looking at so far, the differential kinematics of that, are essentially a velocity Jacobian, and that velocity Jacobian is the gradient that you can use to minimize functions of error for these robots. So in this case, we showed you how we can minimize the error to a desired heading and distance. And this is something that will also work for multilink arms.